I'm Robert Lercari, VP of Engineering at Radian Memory Systems, and my talk today is about Zoned Flash SSDs in advanced storage systems. This is our legal disclaimer. Now here's the agenda for our talk. I'm first going to cover cooperative flash management and zoned flash drives. Then get into configuration of a zoned flash SSD with our ASL functionality using our ASL configurator. I will cover Idealized Flash, and then I'll discuss something called strict write pointers and two of the potential solutions for dealing with them. After that, I will describe garbage collection, including our delegated copy move feature, then a back-channel communication capability being used with wear leveling and NAND maintenance to maintain quality of service over the life of the drive. Then I'll conclude with some results from our apples-to-apples performance benchmarking tests that compare our zone drive to an almost identical FTL-based SSD. Before we get into Zoned Flash specifically, I'm going to start with a high-level overview of cooperative flash management. Cooperative flash management is based upon redistributing flash management responsibilities and functionality between the host and the device. Symphonic was the first implementation in the industry to partition these flash management functions in this manner, where the data placement, control of garbage collection, and scheduling of maintenance operations reside on the host, and NAND maintenance resides on the device. Device responsibilities also included state management, options for configurable addressing, and a zero-copy offload feature to reduce host resource consumption and improve scalability. The easiest way to understand the model is if you assume that you have a log-structured host, where the host already has logical to physical address mapping, cleaning, scheduling, etc., but it doesn't know the specifics about the NAND, and it doesn't want to have to learn those specifics. We want to leverage that functionality that already exists to perform flash management, but we don't want to introduce changes to that host software. And where modifications are required, they should be kept to a minimum. By leveraging the functionality that already exists in the host architecture, the redundancies and double penalties are minimized for a range of variables, from lookups and locking to over-provisioning and write amplification. And because processes are scheduled by the host, the overall system is totally deterministic, which is not the case with a FTL-based SSD. But unlike typical host FTL implementations, like the original open channel implementations, the Symphonic media management is handled on the device with different options for host and device-based wear leveling. Symphonic devices have not supported in-place overwrites, but otherwise presented a standard NVMe API plus vendor-specific extensions for additional commands. Here we show a timeline of the evolution of cooperative flash management and how Radian came to develop its implementation of Zoned Flash. After working on the technology for several years, in 2014, while still in stealth mode, we engaged with some of the industry's leading fabs and demonstrated this new partitioning and redistribution of flash management functionality, including cooperative garbage collection and optional modes for host or device-based wear leveling in a real system, with our Symphonic release V1 using FIO. In 2015, we came out of stealth mode as a company with our Symphonic V2 release. We announced the technology and presented it at FMS. We also gave a talk at the 2015 SNIA Storage Developers Conference on the synergies between cooperative flash management and SMR zones, followed by developing the industry's first Zoned Flash drive in 2017, which we called SMRF, sort of an acronym between SMR and Flash. And that was based on our Symphonic V2 release, but with support for zone report and zone reset commands. And we shipped the first SMRF Flash Zone SSDs to OEM customers in early 2018. In 2018, we released Symphonic V3. Up until then, we had provided host resident libraries for our address configuration functionality, But in this V3 release, we moved all of that functionality from the host resident libraries into the device in firmware. And it became the industry's first software-defined flash solution to provide idealized flash and address configuration in an all firmware implementation. And this is the approach that we took forward with our latest release of our Zoned Flash implementation in 2019. That is targeting the upcoming NVMe Express specification for zone namespaces. With our implementation of Zoned Flash, everything follows the same model that we've been using for several years with our original Symphonic CFM drives, apart from some naming conventions and minor layout differences in the API. We are not in the NVMe Express working group for zone namespaces, but as I said, we've been developing Zoned Flash SSDs for several years. So when the finalized spec is released, we intend to make the necessary adjustments to ensure our product implementation is compliant with the standardized interface. As we go through discussing this various functionality today, I'm going to be speaking specifically about our version 3.0 Zoned Flash implementation. For the purpose of enabling existing host file systems that already utilize a zone block device interface, and because we wanted our NVMe Zone Flash devices to be used with minimal modifications, we developed our Smurf ZBD to NVMe protocol translation bridge. The zone block device interface is more oriented around SCSI and connecting to SATA SAS protocols. This Smurf bridge translates zone report and zone reset commands into NVMe commands. It does it using NVMe vendor extensions. This enables systems using the ZBD interface to perform these commands on our NVMe Zone Flash devices. We are looking into releasing the source to the Smurf bridge potentially under a modified VSD license. Along with the geometry emulation, configurable addressing, or what we call ASL for address space layout, is key to how we provide configurable idealized flash zones. ASL is based upon isolated regions. At first, it might sound kind of like the newly released feature called NVMe sets, but it's configurable based on a range of parameters from performance and isolation to endurance and capacity. It's in part based upon NAND dies, where the user can select configurations to optimize trade-offs, such as between bandwidth and latency or capacity and endurance. And of course, this is very relevant to our multi-client virtual machine environments, providing the flexibility to isolate different users or applications from one another to prevent noisy neighbor interference. This is something we're going to get into more in the performance benchmark section. Zones are based on NAND erase units, or what we typically call NAND blocks, and they come from the same isolated region. In host file system terms, zones can be just thought of as a contiguous range of LBAs that create a segment. With zones, there should only be one layer of cleaning up on the host, and ASL enables the SSD's zone size to be configured to match that host segment size, creating an alignment that minimizes write amplification. With FTL-based SSDs, the host cleans on one segment granularity and the SSD likely cleans on another granularity, creating a dislocation in addition to a log-on-log write amplification. But ASL also enables write stripes to be configured to align with the application requirements, thereby matching performance requirements while also optimizing latency. After the drive is configured, that configuration can be discovered through the zone report command. Our zone drives are configurable based upon performance, endurance, isolation, capacity, and a range of other parameters. A higher bandwidth requires that more dies be included in the write stripe of a given frontier, which implies larger zones comprised of higher numbers of participating erase units. Isolation between zones requires that they be laid across separate dies. And Increased endurance implies a smaller overall capacity due to increased over-provisioning. The assignment of the LBA ranges to groups of flash structures is what we call the address space layout, or ASL. And Radian's ASL configurator allows the user to pre-configure a specific address space layout, such that the frontier stripe width and isolation of individual zones meet the desired trade-offs between the zone size, performance, quality of service, and endurance. The ASL configurator uses a geometry export capability of the Radian zone drives to query the quantity and topology of the flash array elements present in a particular drive. And with that information, the ASL configurator calculates the trade-off possibilities. It gives the user the ability to choose the highest priority attributes, and through a feasibility process, the ASL configurator provides the user with the optimal ASL configuration. The ASL configurator is a tool that we have been using internally for several years to determine what are the optimal ASL configurations given various user criteria. And we use it to program these configurations into individual drives. What you see here are some different screenshots of the tool that is currently in process of being rolled out to our customers for general use. Idealized Flash is provided by geometry emulation, where the device provides the host with an idealized representation of the NAND. This is based in part on Radian's hierarchical address virtualization. Radian zones are comprised of NAND array units that come from the same isolated region. Geometry emulation abstracts that NAND geometry and vendor-specific attributes, thereby presenting the host with zones of idealized flash. Zones appear as a range of contiguous sequential LBAs accessible using conventional addressing through the NVMe command set. Contiguous addressing means that there are no holes in the address space, in spite of non-power of 2 NAND values. The strange NAND attributes and anomalies specific to a given generation of NAND or a specific vendor are abstracted from the host. This means that the host software does not need to account for these details or be modified to support one NAND vendor versus another. As an example, hosts do not need to concern themselves with a cache minimum write size. It's not an FTL. There is no page-level logical to physical address translation or any giant 0.1% storage mapping requirement. It's deterministic, and in normal operations, it does not move data without being commanded to by the host. And one of the real beauties of it, it only requires a couple percent of over-provisioning. NAND flash memory requires programming media sequentially. Hosts that access the media directly on an SSD, such as with a software-defined flash device, as opposed to an FTL-based device, need to write to the relevant addresses, for example, within a zone, sequentially. For this reason, zone drives employ what is known as a strict write pointer. The strict write pointer requires that the write pointer always points to the next available address on the media, such that the LBAs of arriving writes must match the current write pointer of the associated zone. The problem is that various transport protocols support packet reordering. This can occur with fabrics, but can even occur locally with PCI Express. It causes sequential writes to arrive out of order, and it's a condition we call tangled ordering. That's what you see illustrated here, where the host issues sequential LBA write operations to the storage device, but as the LBAs travel through the system over different chipsets and protocols, they don't arrive at the storage device's receive buffer in exactly the same order that they were issued. On devices that are constrained with strict write pointers, this can result in a write error, requiring that the out-of-order writes be reissued. And that could severely impact your performance. There are brute force ways to get around this, where sequential ordering can be guaranteed through the use of single I/O depths or by issuing all writes synchronously. But these approaches are also going to have a severely negative impact on performance. In fact, when we tested strict write performance on a particular closed and forgiving system by enforcing the strict write pointer requirement, we measured an 82% drop in the write rate due to a high rate of kernel retries, and nearly 98% of all the writes failed on their first attempt, requiring at least one retry. One solution is to implement zone append. The idea here is to issue writes to a specific zone and have the device choose the offset into the zone where to actually write the data based on the current position of the write pointer, and then specify that offset or created LBA back to the host. The host then would update its mapping tables so that it knows where the data actually ended up. This approach solves the strict write pointer issue by eliminating write errors due to tangled ordering, and would not require a single I/O depth for each open zone to prevent tangled ordering. But with zone append, the host software or file system needs to be modified, and the extent of those modifications are going to be different for each software stack. For some, it could be straightforward, but for others, there can be issues with new consistency models and with how to handle failures. And regardless of the modifications, there may still be a latency hit when the host is updating its mapping tables. Radian Zoned Flash SSDs do include support for zone append as an optional feature, and our implementation of zone append can support multiple concurrent appends and completions. Correct. Well, what we mean by that is that it could be happening same time and there's sufficient resources that we can not have a problem. The other alternate solution to the strict write pointer problem is a capability we call relaxed write pointers. It is based on the Idealized Flash functionality I mentioned earlier. In addition to overcoming NAND vendor-specific attributes and the geometry and addressing anomalies, Idealized Flash relaxes the frontier of the write pointer. So relaxed write pointers overcome tangled writes and enable the SSD to accept write operations that started out as sequential on the host but arrive at the SSD out of order. The nice thing about relaxed write pointers is that unlike zone append, you do not need to make modifications to the host software, nor do you need to account for new system consistency models or introduce additional latency. And relaxed write pointers don't require a big logical to physical mapping table on the SSD. But the natural question here is, okay, you handle tangled writes, but to what degree? And how out of order can they be, and for how long? The problem and the answer isn't really about how out of order they are. As long as the host is attempting to write sequentially to a write frontier, we can support it by overcoming the tangled reordering that can occur from chipsets and transport protocol reordering. But it does boil down to how many of those write frontiers you have open and what the I/O depth actually is. To give you a data point, our current RMS 350 zone drive, the one being used in our performance benchmarks, can handle tangled ordering for over 800 simultaneously open zones with an I/O depth of 4, with 4K LBA writes per zone. And if we crank that I/O depth up to 32 for each write frontier, the RMS 350 zone drive can still handle over 400 simultaneously open zones. That means that the total device I/O depth can be at least 3,200 4K writes. While it is theoretically possible someone would want to run the SSD at full queue depth, it's not something we've ever seen users actually want to do. And in this extreme example, we'd only need a couple hundred megabytes of SSD storage. In reality, fulfilling most system requirements may not require any SSD RAM at all for relaxed write pointers. But regardless, it's nothing like the gigabytes often required for a full logical to physical mapping table. One of the concepts being discussed around Zoned Flash is having a fixed size that is a power of 2, such as 512 MIBs, which is like 536,870,912 bytes. And because physical flash structures often do not have power of 2 capacities, the defined zones are allowed capacities that are less than the power of 2 zone size. And because physical flash goes bad, the idea is that zones would be allowed to shrink capacity. And so when the host is writing sequentially across any zone write frontier, there can be a sudden write error before the advertised zone capacity is exhausted, where the zone will no longer accept any additional writes. This forces a zone excursion where the host must continue its write on a different zone. In our opinion, this is basically a nightmare for file system designers. Not only would the file system need to now deal with gaps of unusable LBAs between zone capacities, but the size of the gaps will change over time, with zones potentially becoming all kinds of different capacities. Existing file systems were written with the assumption that block devices consist of uninterrupted sequential LBAs from 0 to n, with no gaps and no changes in capacities. Modifying the file system to deal with LBA gaps of changing sizes can be very difficult, require multiple man years of tests and development, and then end up degrading system performance. Idealized Flash combined with ASL solves all of these problems. It eliminates the need for any LBA gaps, such that for every zone that ends with LBA n, the next zone begins at LBA n plus 1. Bad blocks are automatically replaced transparently to the host. Zones never vary from their configured size and capacity. And it only requires a couple of % of over-provisioning. And best of all, no modifications to host software are necessary. As I said earlier, Radian's zone block devices achieve idealized flash based upon geometry emulation. Idealized flash respects the boundaries of the physical flash structures such that isolation between dies and between erase units is maintained. Furthermore, Radian's address space layout control of the mapping of the LBAs over the idealized flash structures without any gaps or holes. The flash characteristics and attributes specific to any particular NAND vendor or generation are abstracted out of the contiguous LBA space. This frees the host from having to deal with these kinds of details that no file system designer ever wants to deal with, while still giving them the data placement control over the physical flash that they do want to control for the sake of parallelism, isolation, and write amplification. So with Idealized Flash and ASL, our zone block devices do not require strict write pointers, and they do not need a zone append capability to handle tangle ordering or for contiguous addressing, and will never burden a host with variable zone capacities and zone excursions or LBA gaps. This dramatically simplifies integration of zone flash devices into existing storage systems and minimizes host software modifications. This diagram depicts a standard garbage collection process with a log-structured host, where a host must reclaim space in the form of empty zones in which it can write data sequentially. This is not specific to FTL-based SSDs or zone flash SSDs. It happens with any SSDs in a log-structured host. Log-structured hosts even have this traffic over the system bus with hard drives. The host must copy whatever valid data is left in the zone chosen to be cleaned to another available zone before it can issue a reset to that chosen zone so that it can be reused. The copying of the valid data requires that the host read that data through the PCI interface into its local RAM space and then write it back down through the PCI interface to a new zone. Again, this happens with any storage device and log-structured host. To address the system overhead, Radian introduced its delegated copy move command. The delegated copy move command is essentially a command from the host to the SSD to physically move data from a source address to a destination address without copying the data back and forth to the host. After the command is executed, a completion is sent back to the host, after which, if the DCM command was used to clean a zone, the host can issue a zone reset command to make that zone reusable. The Radian RMS350 Zoned SSD also contains 4 or 12 gigabytes of user-accessible NVRAM. Not only can this NVRAM be used for caching or logging at the host's discretion, it also responds to the delegated copy move command, such that data can be cached or staged on the NVRAM and then flushed into any flash namespace or zone at will. Or data can be pulled from the flash zone or namespace into the NVRAM upon a command. This delegated copy move command is efficient, it's deterministic, and it's user controlled. So when we use the delegated copy command for garbage collection, rather than reading data up to the host and then writing it back down, we simply command the Radian SSD to move the data internally from source addresses to destination addresses. We thereby eliminate all of the garbage collection traffic on the PCI interface and save the system RAM space and save the associated CPU cycles by replacing the steps 2 and 3 of our garbage collection diagram with delegated copy move commands instead. Here we show how a system using delegated copy move allows for nearly 100% of the PCIe traffic to be only user I/O, with garbage collection copies happening internal to the Radian SSD. When you contrast that to a standard FTL SSD that not only has system-level garbage collection data copies clogging up the PCIe interface, the FTL has its own internal copies taking place for its internal garbage collection. And it's out of the host's control, injecting unpredictable latency spikes and multiplying up the write amplification at the media level. And this is known as the log-on-log effect. With the example shown here, with an FTL internal write amplification operating, say, as low as 2, and the host level write amplification operating, say, as low as 1.5, the overall write amplification is still 3, which forces twice the total number of data moves at the media level as you would have with the Zoned SSD, and thereby cuts the endurance of the FTL SSD by 50%. The reduction of PCIe interface traffic that the delegated copy move command provides becomes even more important in a disaggregated storage configurations where a host stack connects to multiple SSDs in a JBOF and where removing the garbage collection copies for all of those SSDs over the NVMe over Fabric wire will free up bandwidth for better system performance. Radian Zoned SSDs also provide an optional back channel capability, which is an out-of-band communication path that uses the system's asynchronous event notification functionality. The Radian Zoned SSD handles all NAND-ware leveling and maintenance operations internally in a manner that's coherently aligned but abstracted from the host. However, in the event that a maintenance operation is required that may temporarily affect SSD performance, or access determinism, the device initiates a request that the host should service the relevant zones, usually by moving that data at some future point. For instance, if data within a particular zone has become cold or otherwise susceptible to read disturbs, and therefore must be moved, the host is notified of the need to refresh or relocate the data. The host can then schedule the data movement at its own discretion, along with being in control of selecting the destination address. This gives the host the opportunity to control the timing of servicing the maintenance events, and it does it on an event-by-event basis. It's not like these requests are happening all the time, and when they do happen, the host typically has time, days, even weeks, to address them. So if one of these requests occurs, the host can, for example, fold that data relocation requirement into its garbage collection process when it's convenient. And it may not need or want to know the details of why the data needs to be moved, but just that it needs to be moved. The Radian Zoned SSD can be programmed to notify the hosts with requests that have escalating degrees of urgency, where the SSD continues to escalate the request until it eventually reaches a point where the Radian SSD services the request itself. This can result in a latency spike, but it's one that has been forecasted to the host, that the host chose to ignore. Along these lines, the host can make a conscious choice to ignore these warnings or just disable them altogether. While this is the simplest approach for a host, and the events are fairly rare in the first years of use, just as with any SSD, they will start to increase over the life of the drive. So to maintain consistent quality of service over the life of the drive, the host should, as a matter of policy, plan to service the requests. Otherwise, the maintenance and relocation spikes will create uneven latency profiles. But in either case, the data reliability will be maintained, as the device will ultimately not allow the request to go unserviced, which is what enables SSD vendor-supported warranties. A really important aspect to this is that autonomous maintenance data movements performed by the drive never change the logical address of the data. So it's not like Zoned Append, where the device moves the data to a new location and the host has to update its own mapping tables. Here, the logical address stays the same. So even if the device is the one to move the data, the host does not need to update any mapping table. For several reasons, including functional and performance testing, and to provide conventional zones that support in-place overwrites, we designed what we call our block translation layer. It has the same log-structured architecture that you would expect to see in a modern storage management layer. It provides the same type of cleaning and space reclamation, along with logical to physical mapping that serializes random writes into a sequential pattern. And as you can see in the diagram on the right, we're using the block translation layer in this test configuration where we're running two instances of it, one on each of the system's two x86 CPUs, each under FIO in a 7030 workload. And each of the two block translation layers are accessing the same 4 zoned SSDs that are operating in a dual port mode. This configuration is being demoed live over at our exhibit, so if you get a chance, you should check it out. Here we have a head-to-head performance benchmark with our Radian Zoned SSD and a FTL-based SSD from a leading vendor. What's really cool about this is that the two SSDs have identical silicon, making the hardware truly apples to apples. They each have the same NAND array, including the exact same NAND memory and total raw capacity, the same DDR capacity, and the same SSD processor. And maybe not surprisingly, if we were to test these two SSDs down at the NVMe device level, the performance is pretty similar. But it's not very representative of the target system configurations we've been discussing. If we instead test up at the block translation layer, we've got a configuration much more analogous to the target systems. And we're able to emulate a log-structured storage management layer like you'd see in a modern flash array. This also captures what is known as the log-on-log effect that these systems experience when they're running over an FTL SSD. We used one of the most common data center workloads, a 7030 mix with 4K random reads and 4K random writes. That's representative of an application. The block translation layer enables us to see how the zone drive performs, not just with garbage collection, but under a mixed workload that has random in-place overwrites at the application level up above the storage management layer. Even though this is one of the most popular workloads, it's something that we otherwise wouldn't be able to test because zone drives don't support in-place overwrites. What becomes really critical, the really critical variable here, is over-provisioning. Look at the table from the bottom row up. For each Apple, the total raw flash available is the same. It's 4.62 terabytes. And the advertised user capacity above the block translation layer, seen on the top by the FIO workload generator, is also the same for each Apple, 3.23 terabytes. In the example we see here, the total over-provisioning is set at 30%. So the advertised user capacity exposed to the FIO tester is 70% for each Apple. That 70% is a 3.23 terabytes. The other 30% is split between the SSD's internal over-provisioning, and the remaining over-provisioning is available to the block translation layer to be used as free space for garbage collection. The FTL-based SSD's internal over-provisioning is 17%, and the Radian Zone's SSD internal over-provisioning is 3%. This translates into a 3.84 terabytes of advertised device capacity for the FTL-based SSD that is made available to the block translation layer, and a 4.49 terabyte advertised device capacity from the Radian Zoned SSD. So even though the raw capacity is the same between each drive, the total user capacity exposed to the application is all the same. The zone drive is providing much more device level capacity to the block translation layer, and that translates into twice the amount of free space, 27% instead of 13%, for the block translation layer at the same total over-provisioning of 30%. Obviously, this means the system write amplification is going to be far higher with the FTL SSD due to the reduced free space and the effects of log-on-log. The zoned SSD in this configuration provides much better endurance, but it also provides dramatically better performance. So what you see here is the same total over-provisioning of 30% of raw capacity, presenting the same 3.23 terabytes of user capacity for each Apple as we discussed. On the left is the 4.9 latency over a time domain of 1,000 seconds, using that 70-30 mix workload running at 275K IOPS. The FTL-based SSD shown in black that has the same silicon as the Radian Zone flash drive shown in green has an over 15 times higher 4.9 latency. And when we look at the most critical comparison, the graph over on the right, we see how the 4.9 latency scales up for the FTL-based SSD as the IOPS scale, and alternatively, how flat and deterministic the green line is for the Radian Zone flash SSD as the IOPS scale. Note that the Y scale is logarithmic, which kind of hides how dramatic the differences are. In fact, the 4.9 latency variation for the Zone flash SSD is only 3 milliseconds at 200K IOPS and 5 milliseconds at 250K IOPS. But for the FTL SSD, that 4.9 latency grows from 65 milliseconds to 80 milliseconds over the same IOPS range due to the log-on-log effect. Storage applications such as all-flash arrays and hyper-converged systems are typically looking to crank that total over-provisioning number down to 25% or less. And for hyperscale, they're typically trying to go even lower. What you see here is just a small sample set of what we've been running, and we have many tests that demonstrate varying over-provisioning comparing different leading FTL NVMe drives against each other, and other comparison graphs with Zone Flash that clearly show the advantages of Zone Flash drive. So this is my last slide. In the graph on the left, we show what happens when we change the overall provisioning from 25%, from 30% down to 25%. The FTL-based SSD cannot even get more than 150K IOPS. While the Radian Zoned Flash drive, although affected by the lower over-provisioning, still significantly outperforms what the FTL-based SSD could do with the higher over-provisioning of 30%. In the graph on the right, we are showing noisy neighbors. The SSD is configured with 16 namespaces, and each namespace is running a dedicated host with FIO. In this example, the same 7030 workload is held constant across all 16 namespaces, and IOPS are varied on the x-axis. We can see the 4.9 latency with the FTL SSD starts high, rises quickly with increasing IOPS, and tops out at around 175K IOPS. While the Radian Zoned Flash drive is able to achieve 400K IOPS with a dramatically better 4.9 latency. And other combinations of workloads show similar results. So as I said before, we encourage you to come over to our exhibit and see how our block translation layer runs with an FIO 7030 mixed workload above it, consisting of 4K random reads and 4K random writes on two separate CPUs that connect to the same four RMS350 Zoned Flash drives through their dual port PCI interface. Thank you. So the delegated copy move specifies a source address and a destination address. So all a host has to do is specify destination addresses that are sequential for each one of those blocks that it's moving.
So the host actually initiates the process and assigns the address. And
Right.
You will copy to PCI blocks.
Right.
Another question is, what is the minimum size of your zones? What's the total number of open zones?
So the minimum size of zones is driven by the size of the erase units, the blocks. Okay, because they're, well, that would be technically the smallest that you could possibly go. What was your other question?
Number of open zones supported.
So what we've been able to do with our current RMS 350s, we're able to have over 800 simultaneously open zones and have no problem with hitting the strict write pointer problem. We untangle all the writes as they come in.
For the block translation layer, because I'm curious there, the performance so good. Does the block translation layer knows the physical location of each zone? Does the block translation layer in your simulator or your benchmark know the physical location of each zone?
Yes, it does. It knows them as segments, like host level segments. So each zone looks like a segment, and it's just cleaning on a segment basis.
So it's able to do parallelization across all. I mean, in a real world, the OS, the processor wouldn't know that. We can have divergence. Some people use same line.
It depends on the application and the workload itself. And that's part of the beauty of the configurability. Because with ours, you're able to configure how many dies you want in your parallel for a particular zone for how fast the write stripe would go. Does that make sense? So if you want it to go faster, you need more dies to participate.
But the workload is random from the FIO tester. It's synthetic.
The workload is random. If the block translation layer doesn't know the physical address of each
So it does know the physical address of the data, the LBA.
but that's not translated. Doesn't know the PBD.
Pardon me?
Does not know the PBD.
Well, it knows the physical location for block encryption data.
So that's one information that in the real world, the OS would not process.
No, but that's not quite right. It knows the logical address that it wants to put it. And that's where it goes. It goes to that logical address. It doesn't know, it knows about the topology of the flash. And our idealized flash respects the boundaries of all that. But in essence, to the block translation layer, it's just a logical address.
limitation about the right size and the right alignment?
So, no, there is no limitation. You can configure it to whatever you want. But I will say that if you have for larger write sizes, you do start to have limitations on how many open zones you can have simultaneously. But usually that's not an issue, because as your zone sizes are larger and the bandwidth of the write frontier goes up, you don't need that many of them.
Your right frontier can never be smaller than your zone size, or larger than your zone size.
Yes, I was thinking about the other direction. If you allow small writes, for example, packet writes,
How do you deal with drive endurance? So do you rely only on wear leveling, let's say triggered using back channel to the host, or you also do some, let's say, wear leveling on a drive side?
So inside the drive, wear leveling is taken care of, totally transparent to the host. And your other question about the back channel is, if there's a data move that has to happen for, let's say, because it's been sitting there too long and it's just gone cold, and you're going to have retention issues, so it really has to go to another physical location, then the back channel communication path is used at that point. And it's a matter of basically getting coordination with the host. Hey, should I move it now? Do you want to move it somewhere else? What do you want to do? And so depending on the host, its workload, its application, depending on the timing, the host can basically handle it the way it wants to. Or it cannot handle it at all. If it just doesn't handle it at all, then it just eventually happens.
Okay, but on one of the first slides, you had that there is a zone built on top of a number of NAND dies.
Right.
And it looked like a kind of static assignment.
It is static, but it's pre-configured.
Okay, but in case if you have one zone very intensively updated, so written, erased, comparing to another zone which is written once. So how do you deal with this situation to make wear leveling?
In a nutshell, when you have a higher endurance requirement, it's taken care of by essentially using more over-provisioning. So it's essentially additional resources are assigned to that region so that you can incur the greater endurance.
But there will be differences in the wear of the hot zone and the cold zone, right?
Yeah, there is,
The
but
drive is not going to start moving around daytime.
well, actually, the drive takes care of all of that transparently. So even if you do have an area that has a high turnover rate, and we're talking about changing the total endurance over the life of the drive, that's when you mess with the over provisioning. But if you don't mess with that, it still gets evened out.
At the cost of some write amplification.
Well, through methods internal to the drive.
During these tests for quality of service, were you using just random writes across entire capacity, or you used some writes with different lifetimes, some hot and cold zone?
In our tests, the workload has been completely random over the entire advertised space.